Everybody, welcome back to ANCC's lecture series on competitive programming. Today's lecture will be on a bunch of powerful and fundamental algorithms that we competitive programmers use on a daily basis. The last lecture was more about C++ basics, but today's lecture is even more important and contains a lot of fundamental algorithms that are key to mastering competitive programming as a whole. So the first topic that we'll be looking today will be the prefix sum. So we'll first look at this question. You are given an array of integers and multiple times you will be asked this question. Given different values of L and R, what is the value of the sum of elements from AL to AR? So trivially what you would think of is each time we get a query, have a sum equal to 0, and for each element from I equal to L minus 1 to R minus 1, just do sum plus equal to V of L for V of I for I in the range L minus 1 to R minus 1 inclusive. So basically in questions which mentions index, these indices are usually taken to be one indexed. So this is why I've done L minus 1 and R minus 1 here. So let us see what is the drawback of this approach. So each time you're asked a query, we perform an operation R minus L plus 1 times. This is basically the number of numbers that you have summed. So we perform an operation these many times for each query. So in total we perform Q into R minus L plus 1 operations roughly. And in the worst case, L can be 1 and R can be the size of the array. So in total we use N into Q operations. Now in most questions what you would see is the number of value, the range of Q can be anywhere between 1 and 2 into 10 power 5. And similarly N is also between 1 and 2 into 10 power 5. This means that the number of operations we used is about 4 into 10 power 10, which as we learned earlier would take about 400 seconds to run. Too slow. So to improve this, we will be using a technique called the prefix sum technique, in which in advance we do some extra computation, but each time a new query comes, we answer that query almost instantaneously. So the way we develop this technique is one very cool transformation, that is sum of numbers in L minus 1 to R minus 1 inclusive. Whenever you use square brackets, you take it to be inclusive. This would be the sum of numbers in 0 to R minus 1 minus the sum of numbers in 0 to L minus 2. So basically what we have done is, we have transformed this subarray sum problem to a difference of two sums where one of the endpoints of that sum is fixed. So one very nice thing that you can do here is, in advance we will compute sum of numbers in 0 to x for each x in 0 to n minus 1. So how this helps is that okay, first of all, how do we compute this? We can just initialize a sum equal to 0, and as the sum we will store these answers, vector int answers of n, and for int I equal to 0, I less than n, I plus plus, what we can do is sum plus equal to v of I and answers of I equal to sum. So eventually answers of 0 contains v of 0, answers of 1 contains v of 1, answers of 1 contains v of 0 plus v of 1, this contains v of 0 plus v of 1 plus v of 2. So what we wanted here, that is the sum of numbers from 0 to R minus 1, this would basically be some number in the answers array, right? So whenever we want to find the sum of a subarray, what we do is we take two numbers from this answers array and just subtract them. Say we wanted sum from 1 to 2, we would just do answers of 2 minus answers of 0, right? Okay, so in this computation, we would take n operations to run this for loop and compute the answers array. Plus, each time we have a query, we just do a subtraction. We can just take that as q operations, 2 operations. So we have used about n plus 2q queries in total, which is 2 into 10 power 5 plus 2 into 10 power 5 into 2, which is about 6 into 10 power 5, which is way less than 1e8, which is less than 10 power 8. So our solution is blazingly fast. Right. So we'll see one trick which we can use to implement this. So first we will input the array and input the number of queries, and for int query count equal to 0, query count less than q, query count plus plus. Here what we do is we input the lower and upper bounds of our sum. Okay, so we are supposed to compute this answers array, right? Instead of calling it an answers array, I'll call it the prefix array. So vector int prefix sum. Okay, so what I'm going to do here is I will have prefix sum of 0 equal to 0. So why I'm trying to do this is because I need something to indicate that we don't have to sum any values. Say L is 1, we do not have to subtract values from this term just so that we get this sum of values from L minus 1 to R minus 1. So basically I added a dummy value at the start which is 0, and prefix sum of 1 will have v of 0, prefix sum of 2 will have v of 1 plus v of 0, prefix sum of 3 will have v of 2 plus v of 1 plus v of 0, and so on. Prefix sum of n will contain the sum of the entire array. Right. So to compute this, what we can do is we can have an int sum equal to 0 and prefix sum of 0 equal to 0. For each element of v, we can add to our sum v of I, and prefix sum of I plus 1 would be our sum. So if you just do a dry run, for I equal to 0, we'll get sum v of 0, and prefix sum of 1 would be v of 0. Prefix sum of 1 would be v of 0. Right? Perfect. So whenever we get L and R, say L is 3 and R equal to 6, we are actually interested in finding v of 2 plus v of 3 plus v of 4 plus v of 5. Now, yeah, this is just because whenever questions give indices L and R, they are 1 indexed, means they start from 1, but in our vector v, the indices start from 0. So if we want v of 2 plus v of 3 plus v of 4 plus v of 5, what we can do is we can write this as v of 0 plus v of 1 plus v of 2 plus v of 3 plus v of 4 plus v of 5 minus v of 0 plus v of 1. I have basically subtracted v of 0 plus v of 1 here. So this element, this thing is contained, first term is contained in prefix sum of 6, and second term is contained in prefix sum of 2. As we discussed here, prefix sum of 2 is v of 1 plus v of 0, prefix sum of 2 is v of 1 plus v of 0. Similarly, this term will be contained in prefix sum of 6. So prefix sum of 6 is basically prefix sum of R, because R is 6. Prefix sum of 2 is prefix sum of L minus 1. So in total, just to get our answer, we can just do one subtraction, that is prefix sum of R minus prefix sum of, and we print our answer. Is that clear? So basically the whole reason why I added this 0 dummy value was because say L is 1. If L was 1, we don't need to subtract anything. And to signify that we don't have to subtract anything, we'll just put a 0 at the start. So this answer will finally contain the value of the prefix sum. Right. Okay, so now we'll go on to the prefix sum method is quite cool. It helps us answer this subarray sum queries in queries almost instantly. And just like we have prefix sum, we can have other prefix data structures too. We can have a prefix maximum, which is here prefix sum of I was the sum of numbers till I. We can have a prefix maximum, which is prefix maximum of I, sum of numbers till maximum of numbers till I. Similarly, you can have a prefix minimum too. There are all sorts of prefix data structures, and a lot of questions are prefix sum comes in handy in a lot of questions, not just something which is quite so explicit as this. Right. So we'll move on to the next technique, which is our two-pointer technique. So to understand what this technique is about, let us look at this question. That is, you are given an array of positive integers and you have a target x. You have to find the length of, and remember that it is positive, it is not just any general array. We have to find the length of the longest contiguous subarray whose sum remains under x. So what does a subarray mean? Subarray means a contiguous part of an array. And just like we saw earlier, indices from L to R. Similarly, a subarray is some contiguous part of an array where you can delete elements from the start and end of an array and be left with this subarray. Right. So given an array, we have to find this. Okay, what is our trivial method? The trivial method here would be to input n and x, and for each starting index, move the ending index as far as you can until the sum remains under x. So how you would implement that is, for the starting index is 0 to n, send the ending index from I plus 1, send the ending index from I to n, have a sum, increment the sum only if sum is less than equal to x, then increment it, right? Okay, we need to input our elements, vector np of n. Right, if the sum is less than equal to x, we can add v of I in our array, and if it is not, then just break out of this. We don't have to use this index any further. So if this is the case, then we have an okay answer. So best answer would initially be 0, and since we have added an element, we know that our answer might have changed, so we will update the current answer with j minus I plus 1. The ending index is j and the starting index is I, so including I and j, there are j minus I plus 1 elements in the array. So finally we have best answer, which is the longest subarray whose sum does not exceed x. So what is the issue with this approach? The issue is for each value of I, we go for j equal to I, j equal to I plus 1, and so on till j equal to n in the worst case. So in the worst case, this block is executed executed 1 plus 2, n minus 1 plus n minus 2 plus n minus 3 and so on till 1 times, which is n into n minus 1 by 2 times. And if we take n as something as large, n as 2 into 10 power 5, we easily exceed time limit of 10 power 8 operations. So in order to reduce this redundant computation where each time you start a j from I, we have something called the two-pointer technique. So the two-pointer technique does not add anything new as such, but then it saves a lot of extra effort that we are doing currently. So for this, what we have is, so we again have a sum which is 0, and we maintain a right index. So what I'm going to do is, I'm going to say this R signifies one place after the rightmost valid right index after the left index. So in what I'm going to do is, for I equal to 0, I'm going to try pushing R as much as possible to the right until this sum condition gets invalidated, or the R reaches the end of the array. So the reason why I'm doing this signifies one place after is so that suppose the array is empty, suppose the current subarray is empty, then I can just say that if L equal to R, then the subarray is empty, and you'll see that later. So what happens now is, for L equal to, for starting at I, okay, in best answer 0, yeah, for starting at I, can we push R one step forward? Let us ask this question. So while the R doesn't reach the end of the array, while R is less than n, and the current sum plus V of R is less than equal to the limit. So this is like a green flag. If adding R to our sum permits us to stay under the limit, then we can extend the range of values by including V of R. Remember that R was one place after the end of the window. That means V of R is not in the window originally, but once we perform this check, asking the question, saying, hey, if I add V of R, how much will the sum be? And if that sum stays under limit, then we can increment R, and say that this is our new window. So of course we have to add to our sum also. So sum maintains the current sum of values at indices I plus 1 and so on till R. Right. So once this happens, at this point, I comma R minus 1 is the longest subarray starting at I, such that sum of that subarray is less than equal to X. Okay. So we will update our answer. Our best answer would be the maximum between our best answer and R minus I. So why I didn't do R minus I plus 1 here is because I comma R minus 1 is the longest subarray. So R minus 1 minus I plus 1, minus 1 plus 1 gets cancelled. So R minus I is the length of the longest subarray each time. Okay. So next what we must do is, what can possibly happen is that initially I and R are 0. In the next iteration, what happens is, say V of 0 is so large that V of 0 itself is greater than X. Then in the first iteration, we cannot increment R, which means R stays 0 itself, and in the next iteration, we have I equal to 1 and R equal to 0. This is something which is physically quite incorrect. So each time we see that the L becomes more than R, we just set R to become max of L and R. Okay. And finally, while moving from I equal to 0 to I equal to I plus 1, we must definitely remove the I which was in our window. So each time we are trying to compute the longest subarray starting at I, such that subarray is under limit. Next time the subarray would be starting at I plus 1. So we would have to remove I's contribution in the subarray starting at I plus 1. So what we should do here is, if the window is not empty, that is, if V of I is in the window, how do we check that? If L is not equal to R, this means the window is not empty. If L is not equal to R, the window is not empty, and we must remove V of I from our sum. Right. So each time what we have is, at the start of the window, we have a range of starting at I plus 1 and an R which might not be optimal. So this R was optimal according to I and not according to I plus 1. So we start pushing R as much as possible until we reach optimality here also. So at the end what we have is at each iteration we have the best R for this specific I, and we use that R to update our answer. So you might be thinking that this doesn't really save operations. It actually does a lot. So you might be miscalculating the number of operations used by saying this while loop is such that R starts from say 0 and ends at n. So you would use n operations here, and for each I, what if we use n operations? So that is not how you count operations. So one silly mistake here while computing operations is that we see a while loop, see that it takes n operations in the worst case, and just do n into n, which is n square operations. So this is a mistake here. This is not how you're supposed to calculate operations. So what happens here is that in this while loop body, whenever this while loop body executes, R is incremented by 1, which means that in total, since R is always under n, this while loop is executed at most n times, right? And since R cannot decrease here, R cannot decrease here, R is only being incremented here, which means in the worst case we would have R being incremented n times. So you would count the contributions of this while loop as n, not as n square. N in total, like including all the iterations, not only for I equal to 0. So yes, it is true that in the worst case this while loop executes n times, but if the while loop executes n times, then in the upcoming iterations, this while loop would always execute false and it will not use up any operations. So although the worst case is n operations for this while loop, we analyze time complexity of programs as a whole. And as I explained, we increment R each time this while loop executes. So we can't execute this while loop more than n times because we have this R less than n condition here. So this solves our problem in linear time complexity. So number of operations used here would be about n for the while loop body. So this again repeating that the while loop body as in the while loop body added over all iterations for I. So would be n for the while loop body, and it would be 1 here, 2 here, say 3n here, plus 3n. So we will, instead of using n square operations, we use about 5n operations instead of n square, which is about 1e6, 10 power 6, which fits in the time limit. So this is the two pointer technique that we used. That is, it is also known, it is actually the sliding window technique, but yeah, there are 2 pointers here. That is, we have one pointer to signify the start of the subarray, and we actively update the right pointer, that is, which maintains how far the subarray must grow. So this saves the time complexity by quite a lot. That is, instead of using n square operations, our code used 5n operations. This is quite a versatile technique. I would recommend you all to try more questions about the 2-pointer or sliding window technique. And it is quite easy to miss certain special cases, such as this I not equal to R case, where this window is empty but still you're subtracting V of I if this I not equal to R was not there. Similarly, this was a special case too. That is, say the I grows beyond R, then we would have to update R to be I in order to maintain physical consistency. So that is it about the 2-pointer technique.
Right. So, yeah. So let us move on to our next problem. Till now, what we have seen in binary search is that, say you have a sorted array. How do you search for a given specified value in in an in a short in a short span of time. So binary search can take roles even in places where you do not expect it, such as questions like this. So you have n machines, and each machine spends has a different rate of production. That is, um, that is, it takes Ti time to produce one product, and each of these machines have their own specified rate of production. You want to find the minimum time that these machines, while working together, produce exactly produce at least k products, right? So for this, what you can do is, okay, how would you solve this? Say that it was given to you in a math exam. What we would do is, say the required answer is T, is capital T. In capital T time, the first machine produces lower of T by Ti machines. What I mean by this is just divide Ti by T and take the quotient. So if a machine produces two, if a machine produces two products per machine takes 2 seconds to produce each product, then in time T we would have floor of T by two machines. So we would have the same for the second one. Second machine produces this, and so on. So we want to find the minimum T such that summation from I equal to 1 to n of lower of T by T underscore I is at least k. So I do not think it is easy to solve this question, solve this inequality mathematically. If this floor was not there, say we had perfect rational numbers, then it would make sense to just take t common and then send the 1 by ti's ka sum to the other side. But now that we have the floor here, um, predicting an exact t to solve this question might be a bit difficult. So for this, what we do is we just observe one fact. That is, as B increases, the LHS also increases. That means, given a T, if we know that LHS is too small, then our actual answer, say T naught, would be right. If we know that the LHS is too small, then the actual answer would be, of course, more than the time it takes to produce the too small number of elements. And um, say the LHS is large enough, we know that T naught would be less than equal to this T. So this should be giving you a hint of binary search. That is, this is equivalent to saying that T is an index, and at this index, is the value that we have more or less than T. Um, so what we do here is we binary search on the value of T such that we find the first value that satisfies the smallest value of T that satisfies the given inequality. Right. Okay, and one thing we forgot to warn you guys in these questions is that um, although okay, so instead of integers are of multiple types in C++, the standard int that we use can carry values up to 2 into 10 power 9, about roughly. But say if you have 10 power 5 elements, each of this 2 into 10 power 9 value, what that can cause is that this int sum, by repeatedly adding 2 into 10 power 9, the value would overshoot our upper bound. So int cannot actually carry the sum of loads of ints. So for this, what we use is we have another type of integer called the long int, or long for short. This can carry values up to 2 into 10 power 80. And almost all competitive programming problems intend such that the values that you have in the intended solution, those will fit in this limit almost all the time. So one common practice that we competitive programmers use is, instead of saying int each time, either we can say long each time, or we can let C++ do that for us by just saying, hey C++, hash define int long, and we will have to change it. So what saying this does is that each time you call an int in the future, C++ by default assumes that the int is a long. Although this is a bad practice in actual production environments, like say working at an actual system where um, the exact time that your code takes to run is something that matters a lot, then this thing would not be something you would do, something that you do optimally. You would instead see carefully. The values of v never exceed 2 into 10 power 9, so this should be safe. But the values of sum can exceed 10 power 9, so this should be long. And similarly, this should be long block. Similarly, this should be long block. So this is something we must take care of a lot in competitive programming. That is, we should ensure that the values that our data types have do not exceed the maximum prescribed value. Okay, coming back to our binary search question, I hope you have understood the algorithm. If not, we will implement this right away and we'll see how efficient this algorithm turned out to be. So first, say input the number of machines, and then input the target, and initialize a vector of times it would take for each machine to produce a product, or in type 0 less than I plus plus C. Right. Okay. So what we do here is, in binary search, we had an int low three machines, C plus plus. C. Yeah. So this is the actual question. So yeah, for each machine, we know how much time it takes to produce each product. What is the time it takes to produce k products? And in this question, we have that uh, the time it takes for a machine to produce a product can be up to 10 power 9. And the number of products it needs to produce is also up to 10 power 9. This means that even if you have at least only one machine, then in the worst case, you would take 10 power 18 time to produce the key products. So 10 power 18 is actually a safe upper bound of our answer. So we can say high is equal to 180. So we need to see what value in this range is the actual minimum. So for this, we do a binary search. Okay, sir, not int. Again, we need a long log. And here int works. Okay, so here what we do is, we have a middle value, which this is the candidate that we'll be working on. We check if this mid is higher, mid has an LHS, produces an LHS which is large enough or too small. So we'll have an LHS, long LHS. Okay, writing long each time is becoming too tiring. I'll just do hash define it long. So let us say the LHS is 0 for now. We have to sum in the LHS the contribution of each machine. So for int I equal 0, I less than I plus plus, LHS plus is equal to mid by T of n. So by default, C++ does floor division automatically. You do not have to explicitly write floor of T by Ti. This already rounds down to the quotient, right? And one thing we need to be careful here is that um, it is possible that LHS exceeds 2 into 10 power 18 also, which means long isn't sufficient to contain LHS itself. In that case, what we can do is we can put a check here. If LHS is more than 280, just declare that this is okay. What I mean is okay is bool is LHS large enough. If the LHS is more than 218, and we know that the RHS is only up to 189, is it? Yeah, RHS is only up to 189, so we don't even have to do 218. We just put something like 289. If the LHS is more than 289, we already know that the LHS is large enough. Is LHS large enough? This would be true. And we would stop adding to LHS and we would just break here. So if the LHS is large enough, then our search space would now be from mid to high. We don't need the range low to mid -1 because we already know that mid is an answer that works. That mid produces an LHS which is large enough. So we set our low to be mid. If the LHS is not large enough, then we might have to do some extra effort. That is, we just need to check if LHS, the number of machines that mid produced, is greater than or equal to K. K is the target. And this is the same case as LHS are large enough, so we know low equal to mid here. In this case, oh sorry, high equal to mid here. Apologies for that. Right. So we are searching for the minimum value of t which satisfies this equation, right? That means if we see a mid that satisfies our answer, we do not have to care about values which are greater than mid. Because if mid satisfies that answer, we already know that values greater than mid satisfies the answer. And we are not even interested in those values because we want a minimum such value which satisfies the equation. So if the LHS is large enough, our search space would be in low to mid. We know that mid satisfies the answer. We don't know if anything will be low to mid satisfies the answer. So we keep searching in that range. So here we set high is equal to mid. Here we set high equal to mid. And in this case, LHS is clearly not large enough. And we need something clearly larger than mid. So we will set our search space ka lower bound to mid plus 1. So finally, when this terminates, we will have low equal to high is equal to the minimum such t such that the summation from I equal to 1 to n of floor of capital T by Ti is greater than equal to x. Is that clear? So we just print see plus I'm just checking if I did something wrong here. Yeah, this seems to work fine. Yeah. And one thing you need to be careful here is that it is possible that your binary search runs into an infinite loop because say you forget to do +1 here. What can happen is low can get stuck at 3, high can get stuck at 4, and mid will be 3. So your low gets updated from 3 to 3 itself, and this while would always be true. So it is important that you have at least one of these conditions to reduce your search space. else you can end up in infinite loops. So this is a technique which we call binary search on an answer. We do not know the exact answer beforehand, but we know that if you're given a candidate, is that we can check easily if that given answer is a valid answer or not. So here we had mid as a candidate. We checked how many products this candidate produced, and if the candidate was good enough, we took it as acceptable and narrowed down our search space accordingly. So let us do an analysis of the of how many operations it would take. This whole thing would just take about some, say, 5n operations. 5n operations. And this while loop, so as we discussed in the earlier lecture, binary search reduces our search space by a factor of 2 each time. So this executes log base 2 of high minus low times. So log 2 of 118 would be 18 into 3, about 60. So this in total runs about 60 n operations. And we are in the question, we are given that n is after 2e5 and 60 n is of about 1e7 or 1e8, and that should pass fine under the given constraints. So this is about binary search and answer. This is a very useful technique. You can see problems of varying difficulty where binary search is not even obvious. At least here it was obvious. It was kind of understandable because given a candidate T, can we check if this is valid or not? There might be problems in the future which we will discuss in this lecture, in fact, where binary search of the answer is the actual method to use, but it is not evident at the start. Okay, I hope you liked this approach which I just shared. The next thing we'll be discussing is I give you an intro to how a binary system works and about um, bitwise operators, and basically. So most of you already might know this, but for those of you who don't, you can convert any number. You can represent any number as a sum of powers of uniquely as a sum of power of twos. Uniquely as a sum of power of twos. For example, say you have 33, you can write 30. Say you have 35, you can write 35 as 32 plus 2 plus, sorry, 32 plus 2 plus 1, which is 2 power 5 plus 2 power 1 plus 2 power 0. So say you want to write a program which tells you what this power of 2 representation is. So before that, what this power of 2 representation means is it is actually the binary representation which computers use under the hood. So how you would write 35 in binary, say 35 is an 8-bit integer, meaning we need 8 powers of 2 to represent 35. Then, since it's 2 power 0, since we've used 2 power 0, the rightmost bit would be 1. Since we have used 2 power 1, the next bit after 2 power 0 would be 1. We have not used 2 square, so that could be 0. We have not used 2 cubes, so that could be 0. We have not used 2 power 4, that could be 0. We have used 2 power 5, so that would be 1. And these would just be zeros. Right. 1, 2, 3, 4. Yeah. So this is the base to binary represent. This is the binary representation of 35. And bitwise operators are basically operations that you perform by sort of um, combining / operating on each bit one by one. Okay, one by one. So I'll tell you in a moment what I exactly mean by that. So let's take another number, for example, say 17. 17 is 16 plus 1. So we would write that as 0, 0, 0, 1, 0, 0, 0, 1. Yeah, this is the binary representation of 17. Okay, so there are a few basic types of bitwise operators. The first one is the bitwise AND. So what the bitwise AND does is it visits each bit of, it takes two numbers, that is A and B. It visits each bit of these numbers, and in the result will be 1 if and only if both these values are 1. So to do a dry run, we have 1 and 1. Both these values are 1, so we put a 1 here. We have 0 and 1. Both these values are not 1, so you have a 0. So exactly the name suggests, if both of them are 1, then we put a 1, else we put a 0. So as you can see, at the same bit, no, we don't see any other place where there are all ones. So we have 0, 0, 0, right? Similarly, we have the bitwise OR operation. In the bitwise OR operation, the result contains a 1 if at least one of the two operands has a 1 at that position. So at the leftmost position, there is no such 1. At the next position, there is no such 1. In the third position, there is a 1. Fourth position, there is a 1. There is no 1 after that. There's no 1 after that. There is a 1 after that. There's a 1 after that. So A and B would be this, which is 1. A or B would be this, which is 1, 3, 19, 19, 32, 51. Similarly, we have the XOR operation. The XOR operation is A XOR B, which has a 1 if exactly one of these is 1. So you can see that this would be 0, 0, 1, 1, 0, 0, 1, 0, which is, I don't know. Yeah. So bitwise operators is basically operation that you perform bit by bit on the two operands that you have in order to get a resultant, which is also, and we mostly work on integers here. So let us look at this problem first. Okay, before that, I'll tell you how to convert stuff to binary in case you've not done that before. So the way you convert stuff to binary, say you have a number, say 18. What you do is you divide this by 2. The quotient is 9. The remainder is 0. Put the remainder here. Now take 9, divide this by 2. The remainder is 1. Put the remainder here. After dividing, after dividing 9 by 2, you have a 4. So once you have a 4, you divide by 2, you have a quotient 2 and a remainder 0. So you put a 0 here. After this, you have a remainder 0 again and a quotient 1. And since you stop at a quotient 1, you just put a 1 here. So 18 would be 1, 0, 0, 1, 0. And you can add as many zeros at the start as you want. So this is how you can convert stuff to binary. We will be using that to solve this problem, in fact. So what we are supposed to do is, given an array of positive integers, we want to find the sum of XOR of all pairs. That is, for each I less than j, we want the sum of all v of I XOR v of j. By sum, I just mean simple relation. So I want v0 XOR v1 plus v0 XOR v2, and so on all such pairs, vn minus 1 XOR vn. Yeah. Right. So if we were both here trivially implement this, this would take n square operations, because for each I we need to visit each j. So the trivial approach takes n into n minus 1 by 2 operations. And yeah, which is too slow for our like. So there's a way to optimize this. So before we optimize this directly, let us look at a simple problem. Say v of I, say v contained only zeros and ones. Then what would be our answer? So if v contain only zeros and ones, say 0, 0, 1, 1, 0, 1, 0, 1, then the sum of v of I XOR v of j across all pairs would be what? So what we can see here is v of I XOR v of j is 1 if exactly one of v of I j is 0, else it is 0. If both are equal, they're 0. And so v of I XOR v of j is 1 if they're different, else they're same. So we want, so this sum is basically the number of pairs such that I less than j and v of I is not equal to v of j. Right? So this is basically the count of ones into the count of zeros. And why that's the case is because, for each For each pair that is different, we would count 1 0 for, say, for 1 0. We would like to count the contribution of this pair 1 0. We would count that exactly when I equal to 2 and when j equal to 4. So we basically want the number of ways to select two numbers, two indices such that they have different values, which is so number of ways to select the 0 index would be count of zeros, and the number of ways to select the 1 index would be count of ones. So how does this help in order to solve our problem? So this is a simplified version problem, that is, V contains only zeros and ones. What we can do here is we can solve this original problem. We can solve the above problem bit by bit. So what that means is we can consider each bit of the vector V. By bit, I mean this, say like this. So I can split the problem into multiple subproblems. Say that we can have the first problem to handle the rightmost bit of all elements. The next problem can handle the second rightmost bit of all elements, and so on. So where was I? Yeah, we can solve the above problem bit by bit. That is, the answer to our question would be summation of, okay. So the contribution of the rightmost bit in our answer would be 2 power 0 into answer of rightmost bit. The contribution of the next one would be 2 power 1 into the answer of, so let's say, second rightmost bit, and so on. Right? So solving problems which involve XORs or any bitwise operations in general can vastly be simplified if you look at the problems bit by bit. Instead of computing the final answer at once, we can iterate bit by bit and see how much each bit contributes. Here, the rightmost bit contributes by a weight of only 1. The second rightmost bit contributes 2. The next bit would contribute by a weight of 4. The next bit would contribute by a weight of 8, and so on. So, to implement this, we would first make a function which converts, which, okay. So let us plan first. We'll first take our input, select our P of n, and we'll make a helper function which tells us what is the solve for the solve subcall. So solve subproblem would be a function that we'll implement that tells the answer, say V contains only zeros and ones, what is the answer for this subproblem. So solve problem would be, say, int count of zeros is equal to 0 and ones is also square. And for int I equal to 0, I less than n, like the spreads. If V of I is a 0, then increment the count of zeros, else increment the count of ones. And we would return zeros in tokens. Right. So this would be the answer if if V contained only zeros and ones. So how would we solve if V does not contain only zeros and ones? So we would iterate for int bit equal to 0, bit less than 32. See, so say all of our numbers are 32-bit numbers. If they're smaller, we can just add extra zeros at the left to say that they're a 32-bit number. So for int bit equal to 0, here we solve the subproblem on the bit from the right. So we will collect what is the we will collect all ones and zeros which represent the a bit from the right for all the numbers. So for this, one very nice trick that we can use is for int I equals 0, I is in I equals plus. Just push back v of I mod 2. And for the next time we'll access it, just divide v of I by 2. So this is exactly what we did here. For the leftmost bit, we just did where was that? Yeah, for the leftmost bit, we just found the remainder when divided by 2. And for the next time, we took the quotient. The quotient was this, and we found the remainder of that. And for the time after that, we took a quotient again, and we took a remainder of that. So essentially, each time, binary V contains the equivalent list of zeros and ones if only the bit was there. So we will have an answer. Right. So what is the weight of this answer? As discussed earlier, we would add 2 power 0 we would multiply 2 power 0 for the rightmost bit. For the second rightmost bit, we would multiply 2 power 1 and so on. So the weight of our answer would be 2 power that. So the way you write 2 power n in C++ is you have 1 LL left shift bit. So left shift is another bitwise operator. What it does is, in the binary system, say you have 1, you shift 1 bit number of times. By shift, we mean, so left shift means add bit number of zeros to right. So the weight of this answer would, and you can see that 2 power bit is nothing but 1 followed by 0 bit number of times. So the weight of this answer would be this, and the contribution would be the weight of our answer multiplied by the solve subproblem on this binary V for let Like, so finally, our answer contains the sum of XORs of all pairs from such that I less than G, and yeah, so answer finally contains what we wanted. So instead of having an n square loop, we just iterate 32 times throughout the vector, and we solve the subproblem for a vector of size n which takes n operations. So number of operations used is about 32 into n, which is 32 into 10, 2 into 10 power 5, which is less than 1. So this is a perfectly valid solution. And this was it for bitwise operators. I hope you have understood the bitwise AND, bitwise OR, bitwise XOR, and how we handled the question by analyzing the question bit by bit. So this bit by bit approach can be seen in a lot more trickier questions too, and it is a very important method to keep in mind while solving questions involving binary representations. Okay. So the next method we'll see is not exactly a method, but it is a class of problems called greedy problems. So greedy problems are not like you have a certain fixed method which you use to solve all kinds of greedy problems, but it is a kind of technique which we used to say that, say you have n events that happen in a row, we can choose a sort of best event each time without destroying the effect of future events. And by choosing the best event each of the n times, at the end we have the best result we can have possible. So to give you an example, say you have n activities, and each of these activities have their start at n times. So you can, as a human, you can only do one activity at once. You want to find the number of activities, you want to partake in the maximum number of activities, but you don't want these activities to overlap. So for this, you can have multiple ideas that you might think of. The first idea that you might think of would be, Shorter activity is always better because you can fit much more activities than you would do if you had only longer activities. So while this might make some sense, it is easy to find counter examples to this. Um, say you have a movie which starts at 1 and ends here, and say you have another show which starts here and ends here. So the brackets represent the starting and ending times of the show or the activity, and say you have another movie which starts here, right? So if you say that shorter activities are always better, you would only pick activity 2 and not do either of 1 and 3 because 1 overlaps with 2 and 3 also overlaps with 2. So in theory, you could have done activity 1 and then done activity 3. But then since you thought the shorter activity is always better, you ended up with a suboptimal answer. So another idea that you might think of, idea ideas that make me wait less are better. So what I mean by that is, at the first instant, you see that this activity does not make me wait, so let me just do this activity and keep doing this activity until it ends. After this activity ended, see, oh, this activity already commenced, so I can't use this. The next activity, yeah, this activity doesn't make me wait, so we will do this. So this solves the problem of the first test case, that is, um, solves the about test case by by we use a term by greedily choosing the activity that begins earliest. So what can happen here is just because an activity starts early does not mean that it ends early. So what can happen is, say you have like this, and then say you have an event immediately after this, which takes a huge amount of time. And say you have multiple shorter events here. So what you could have done is you could have done activity 1 and then jump to activity 3, activity 4, and activity 5. But since you stuck to this idea, you would have waited the least amount of time and done just activity 1 and 2. So idea 2 is also suboptimal. So now most of you might be thinking of the correct idea, that is idea 3. Um, sorry, instead, yeah, events that end first are best. So it doesn't matter how long the duration is, we are only concerned by the time at which the event ends. So you can imagine that if an event ends early, that is, say you can partake in an event and that event ends early, ends earlier compared to some other event, then you have more room to fit in other activities just because your event ended earlier, no matter how late the event started. So this is actually the best strategy. The proof is quite straightforward. Um, so the strategy would be start at 0, start at 0, pick the start at t equals 0, pick this event with starting time greater than 0 and minimum ending time, say t1. After picking this event, we can move on to picking the next event. Pick the event with the starting time greater than t1 and minimum ending time, say t2. And we continue like doing like this until all of our events have been exhausted. Right? So, okay. So to solve this question, we would need to employ some data structure which has some sorted order of intervals. So you might be thinking of just using multiset, but just to stick to simplicity, I'll just use a vector for now. So say you have n intervals, C and n, and for each n. So I need a vector of pairs. The pair's first element will contain the starting time. and the pairs end element will contain the ending time. So I would input time slot first and time slot second. Right. Yeah, times of I dot first, times of I dot second. So we have successfully taken in the input of the intervals that each activity has. Once we have done that, so as I said here, pick the event with starting time greater than this. Pick the event with that starting time greater than this. So we would prefer to have some sort of sorted order. Um. Uh. Yeah. So we would have a sorted order such that we are sorted by ending time. So that we pick events that end earlier before events that end later. So we would sort the times array um using a custom comparator, because by default C++ would compare the first element and then the second element. One easy way you can avoid this is to store this in reverse. So now we exactly have what we wanted. So we have events sorted by end time, right? So what we do from now is we have a current time which tracks the current state of whatever events we have chosen. Um, and then we will iterate through this times vector. For and wait for 0, iris 10 times dot size. We will iterate through this vector and then check, does times of I have a starting time more than the current time? Yes. If it is a yes, then we sit through this event. If it's a no, skip this event. So you can see the importance of sorting by the end times. So since we sorted by the end times, we always process events that end earlier before events that end later. And events attended 0. Okay. So to check this, we just have to check. And remember that times of I ka second element was the starting point and not the first element. So if times of I dot second is at least current time, then we can attend this event. So we can increment events attended and we can set current time to the end of this event, which is times of I dot first. Okay. So if times of I dot second is less than the current time, it means we have no option just to skip and we don't do anything here. The current time doesn't change, the number of events attended doesn't change. So at the end, finally, you have the optimal number of events attended, because you always um, prioritized attending events that are ended earlier compared to events that ended later. So this is one type of greedy algorithms. One type of greedy algorithm. Greedy algorithms can come in all sorts of shapes and sizes. Um, they form. They can have potential to form some of the toughest questions that appear on code forces. This is the introductory greedy algorithm which we use. And most greedy algorithms work on some sort of hypothesis or invariant. Just like we progressed from idea 1 to idea 2 to idea 3, progressively getting better. In general, greedy algorithms work in the same way. We, uh, we propose some sort of invariant, try to prove it, and make the most out of what we have proved. So here we just sorted based on 10 times and processed them in that order. And finally computed the answer that we wanted. So this took just big O of n log n time. It is both efficient and correct. Right. That completes our introductory section on greedy algorithms. Our next topic is quite interesting. It has a really fancy name. It's called ternary search. So as the name suggests, you might expect ternary search to be quite similar to binary search, and it is quite similar. binary is effectively representing a 2, while ternary represents 3. So the main use case of this function is, say you have some function like this. I have the graph of this function. So this is a unimodal function. What I mean by unimodal is it has a slope which is changing in exactly one direction. That is, the slope is continuously decreasing in this example. So we have a downward parabola here. So we do not, so in advance we do not know what the downward parabola is, but we would still like to find out what the maximum value of the parabolic function is. So this is not just for parabolas. Parabola is a really special case of unimodal functions, but this method of search works for any function where the values of f appear to have the unimodality property. That is, the slope of the function that it represents has a monotonic order. So here we have an upward parabola. We are interested in finding what is the where the tip of this parabola is located. So for this, what we do is, I'll first give you an outline of this algorithm. So first um, we initialize a search space. Our search space is essentially we something that we know for sure. That is, we know that the tip of the parabola is between L equal to 0 and L equal to 10, say. You might not always know this, but you can give some rough estimates of where the tip of the parabola always is. Now what we do is, we narrow down our search space until the only point that is left in our search space is the vertex. Right. So how this algorithm works is, in binary search, what we had exactly one midpoint. So you might already know why binary search would not work here. It is because, say we have some mid, say here. We do not know if the mid lies in the decreasing part of the parabola or in the increasing part of the parabola. So we do not know which of these um, which portion of the search space to prioritize in order to find a vertex. But now that we have ternary search, what we can do is we can we can do some casework which allows us to eliminate um, certain big chunks of a search space one by one. I'll show you what I mean by that. Um, so what we do is, while the difference between the high and low is some significant quantity, say 10 power minus 6, what we do is, instead of taking the single midpoint, we take two midpoints. So see, I can take the first midpoint to be 2 into L plus 3 by 3, 2 into L plus R by 3, and we can take the second midpoint to be L plus 2 into R by 3. So I effectively divided the search space L to R into three parts. That is, the first part from L to M1, the second part from M1 to M2, and the third part from M2 to R. Okay. And let us evaluate. Okay. So from here we have three cases. From M1 and M2, we can extract the values of f of M1 and f of M2. Right. So first case is if f of M1 is greater than f of M2. Okay. Let us look at this graph. Say R equal to 4, L equal to 0, and M1 is the green point, say, and the M2 is the blue point. So we know that since f of M1 is greater than f of M2, we can have two cases for M1. That is, yeah, that is, M1 is either the red point or the green point. So by red point, green point, I just mean if the red point lies in this range or the green point lies in this range. So there are two cases. That is, for f of M1 greater than f of M2, we can either have the green point or the red point. So if we have the red point, what we cannot just, you understand that we cannot just narrow down the search space such that we search only between M1 and M2. So these are M1 and M2. Narrowing down the search space to M1 and M2 would not always work because we would miss the vertex if we do so. But if we can narrow down the search space if it's the green point. But while evaluating f of m and f of m2, we do not know which of these points it is. But we know for sure that this thing lies in the decreasing portion. This blue dot lies in the decreasing portion of the parabola. That is, if f of m1 is greater than f of m2, it must be such that m2 belongs to the decreasing portion of the parabola. So since it belongs to the decreasing portion of the parabola, we can eliminate the range m2 to r. Does that make sense? So if yes, yeah, if f of m1 is greater than f of m2, we can eliminate the range m2 to r because m2 lies in the decreasing portion, and we know that because m2 to r lies in the decreasing portion, and we know that a vertex does not lie in this strictly decreasing portion. Right. So another case would be that f of m1 equal to f of m2. If f of m1 is equal to f of m2, then we can be certain that um, the the green dot and the blue dot are such that they belong to the two different halves of the parabola. So say a half is divided by this line. If the values of the function are same for m1 and m2, we know that both of these m1 and m2 should belong to different halves. Since they belong to different halves, we know that the vertex would always be in the range m1 to m2. So we can just narrow down our search space to the range m1 to m2. So here, if f of m1 equal to f of m2, we can eliminate these both m2 to r and l to m1 due to a similarity set. And conversely, if f of m1 is less than f of m2, we can eliminate the range L to m1. So it is very important to make these cases each time you see a question which involves some unimodal function in which you have to find some maximum, because this might not be always the case. The exact case that I described works for say the downward parabola. For the upward parabola, these cases would be exactly inverted. So to implement this, we can do int fm1 would be f of m1 and int fm2 would be f of m2. Double view. And for the first case, we have if fm1 is greater than fm2. Then what we would do is we want to eliminate the search space m2 to r. The way we can do that is we can just set r equal to m2. By setting r equal to m2, our new search space becomes l comma m2, which apparently eliminates search space m2 to r. So if this condition is not satisfied, we'll check the equality conditions. If they're equal, we will apply both these narrowings, that is set both L equal to M1 and R equal to M2. And else we just set L equal to M1. So finally what happens is this L and R repeat many times. Initially L equal to 0 and R equal to 4. Maybe after one step L becomes this. Maybe after two steps R becomes this. And so L and R become closer and closer until finally we are left with only the vertex in the remaining search space. So at the end, we have x equal to L as the vertex of the map. And we have successfully completed our done research. Okay, so I have just one very good problem that I would like to discuss, but it does not teach you anything new as such, but it is just a really good problem technique which covers almost everything that we have learned so far. And this will take a bit of time. It would take easily about 20 to 25 minutes. So I would like you guys to try this problem yourself, and I will be sending hints in the groups one by one at regular intervals. And using these hints, you can try to make more progress towards this problem. This is a really nice problem. So just to give you more clarification, a median is in case of odd elements. Median is just the middle element, the sorted order. In case of even elements, um, minimum of the two middle elements in sorted order. So write down this problem. This is a really nice problem. I might be sharing the solution later in the WhatsApp group, but till then, please do give a good try to this problem. And I hope you enjoyed today's lecture. And I have more homework for you. That is, complete the remaining questions of the sorting and searching section. And in conclusion, we have learned a lot of nice techniques today. That is the prefix sum technique, the prefix minimum technique, the two pointers technique, binary search and answer, binary representations, greedy techniques, ternary search. And I wanted to take one more problem, but seems like we're running out of time. So that's it for today. And I hope you're enjoying the lecture series and looking forward to this lecture series in the future too. Okay, bye bye.